Gil, Maria, can you get us? Can you give us a signal? Make sure this is what we
realize certain things.
Can you hear you?
And what was the same thing for us?
I'm testing, but let me test again just in case.
Hello, hello.
Yes, hello. We can this is good. Let's start the photo again. Okay, we need to cut.
Conradie.
Roddy?
No. Okay. 15 minutes.
15 minutes. 15 minutes.
Five
Okay.
zero.
Okay.
Sound good? We're ready to start.
I'm ready.
Okay.
They're ready.
Welcome everybody to the session. We're getting ready to start, so please have your seats. I'm pleased to introduce Willem Conradie from the University of the Witwatersrand in Johannesburg, who will speak on temporal logic of trees.
All right. Thank you so much, Dexter. And thank you firstly to the organizers, Giuseppe, Alessandra, Apostolos, and everybody else. I'm missing somebody. Nahum. Oh, yeah, another. Okay. Thank you so much. I mean, I think this organization has been exceptional. It's a very complex operation, but I think it's gone so smoothly, and it's been such a pleasure to be here this week. So I'm talking on some joint work with Valentin Goronko and Chantal Marais. Chantal did a PhD with me in Valentin. She graduated last year. And this is an ongoing project on the temporal logics of classes of trees. So, get this to go down. How do I do that? Now? Oh, there we go. Okay. So what do you mean by a tree? So a tree is a strict partial order that is left linear. So that means that any 2 points with a common upper bound are comparable. So in other words, I can't have a situation like this. So if we go backwards, so my trees will grow upwards. So sorry, left also means down. Or downwards linear would probably have been a better term. And so this is disallowed. And connected in the sense that any two incomparable points have a common lower bound. So if A and B, neither is related to the other, then there must exist a point which is related to. So we don't require trees to have roots or leaves or to have any specific cardinality or anything like that. Only a partial order with these properties. And what we're interested in is these trees seen as flows of time. So the idea is that if we stand over here, the past is already determined, it's already happened, so the past is linearly ordered, but we don't know what's going to happen in the future, so that branches and these branches of the tree from this point represent these different possibilities. So depending on one's assumptions, you might want to make restrictions on what these trees look like. And so we are interested in any consistent combination of these properties. Should the states be reflexive, irreflexive? Should we be discrete, locally finite, by which I mean between any two comparable points there are most finitely many points, dense, well-founded or conversely well-founded, unbounded in both or in one direction, or we might want to have particular number systems so that every branch is isomorphic to a copy of the real numbers, for example. And what temporal properties in the various temporal languages would be validated by classes from these tree classes. So we will start, so I'll be focusing on the simplest possible language that one could possibly call a temporal language when interpreted on these trees. And this is essentially the language of tense logic. So we've got, we're on a classical base. So we've got the normal propositional connectives, and then we've got two modalities, P and F, for sometime in the future, sometime in the past, and sometime in the future. And of course, we can define their duals as well. The box of the F is G for going to be, always in the future, and the H, the dual of the past, for it always has been. That's I like to remember it. And then we also have two useful abbreviations. This A, which is an abbreviation for it's phi now, it always has been phi, and it always will be phi. So it's as it was in the beginning, is now, and ever shall be. And then this is an existential analog of that. So I'll go through this the slides I'm using were also for a more general audience at some point. So some of this I will be able to go over quite quickly for the present audience. A frame is a normal Kripke frame, as we know. Two pieces of notation, the direct image of a set under the relation, set of all successors of X, and the pre-image set of all predecessors of the elements. Model, we add evaluation on top of this, and the semantics is absolutely standard, so I won't spend time on that. The F, well, F of phi is true at W if there's a successor of W, V, where phi is true, and P is true if there's a predecessor where phi is true. And so consequently, the G, if all successors make the argument true, H if all predecessors make it true, and the A if all, the A phi will be true at W if all states comparable to W make phi true. So everything in the future from W and everything in the past. So it's everything, if this is W, it's everything downwards and everything upwards. But of course, it will not include things that have branched off in the past. So only things in the actual past and in the possible future of W. Okay, so we have different, so that's the simplest language. Then there are two richer languages that I'd also like to consider briefly. This hierarchy of three languages comes from the work of Arthur Prior, and Prior thought of this language as capturing the view, this philosophical view of time in the works of William of Ockham. So what we add here, so we still have exactly the same language, but what we add here is a quantifier over branches. Okay, so a branch or a history, which would be a maximal linearly ordered subset of my, but it's a branch in the normal sense that we think of trees. So the semantics for the propositional part is the same, but what changes is that we interpret statements here. There's an extra parameter, namely a branch or a history. So whatever we say is not just relative to a point in the flow, but also to a particular history in this flow. And this is related to this notion that there is an actual future. So that there's this thin red line that runs through. We don't know which is the actual future, but there is an actual future. And this is useful if you talk about things like future contingent. So future statements about something that could or will contingently happen in the future is then true if it is true in the actual is a future that there is going to exist. So everything gets relativized to both a state and a history through that state. And what the diamond adds here is a quantification over histories through the current state. So the diamond is a quantifier over histories. So diamond phi is true at T, at history H. If for all histories H prime through T, it is the case that phi is true at T. So you can also then generalize valuations here so that a valuation doesn't just depend on the state where you're standing, but also of the history through the state. We won't use that a lot, but it will be useful to be able to refer to this at some point. Now, an intermediate language between the Priorian language and the Alchemist language is the Persian language. So where and it can be seen as a fragment of the Alchemist language because we restrict, sorry, I touch this thing too hard and then it thinks I'm clicking it. What we do is we restrict the use of the modality, this branch quantifying modality, so that it always has to be directly in front of either a P or a F. So this allows me to say that, well, there is some branch through me such that in the past on this branch, phi is true. So this is just exactly the same as the past in the prior. It doesn't add anything because the past is linear. But for the future-looking modalities, what this introduces is a sort of a well, first here we've got the same quantifier. At some state in the future, at some history in the future on that history phi. So that's again exactly the same as the Priorian F, but here we really are different because here we introduce this quantifier alternation. At every history through me, on that history somewhere in the future, phi is the case. So if we have that, we're saying that I'm standing here, and every history through me, at some point, phi needs to become the case. It doesn't have to be there always, but it has to happen. And this is clearly something, I mean, you can prove that, but it's clearly something we can't say in the Priorian language. And similarly, if I was looking at box F, sorry, there is a history, the dual of this, that would mean there is a history through me, which is always phi. Okay, and this is actually very useful because it would allow us to define properties of branches. So if you remember, we were interested in trees, for example, with branches isomorphic to a particular number system. Now I can talk about what happens on a branch, on every branch. So that's quite useful. We can't do that in the Priorian language. Notions of validity, satisfiability, consequence, I don't think I need to rehearse that. All right, so this is the start of our logics. So I'm going to give a couple of examples of logics that we have axiomatized in this setting and how we went about proving the completeness of it. So by a normal temporal logic, we will mean a set of formulas. This is all in the Priorian language, which contains all propositional tautologies. Contains the K axioms for both the future box, the G, and for the past box, the H. Has the expected interaction axioms. P implies box diamond P, so that these are inverses. Future box, past diamond, which ensures that if these were interpreted with two different relations, the two relations would coincide. Well, one would be the inverse of the other side. Modus preclosus under modus ponens, under uniform substitution, and under G generalization, and also H generalization. So that's what you would expect. We call this KT. It's the minimal normal temporal logic. Tense logic, in fact. Sound and completeness, again, for this audience, I don't need to go through. So first, I'm going to present to you the logic of the class of all irreflexive trees. Okay, so this is the logic where we take the minimal logic we had on the previous slide, and we will add to that transitivity and no branching to the left, which is if I've got a P predecessor and a Q predecessor, then these two need to be ordered. Either I've got one which is both P and Q, or I've got a P1 which has a Q in its past, or a Q1 which has a P in its past. So that's canonical for no branching to the left. And so this logic, so adding these two axioms to the basic tense logic, we'll call PR basic because it forms the basis of all of the other logics that we study. And this is strongly sound and complete with respect to the class of all irreflexive trees. And this is how we go about doing it. We do the absolutely normal story. We take a PR basic consistent set of formulas gamma. I need to show that it's satisfied somewhere in an irreflexive tree. So we take the canonical model, normal, no surprises here, an instant in the canonical model where gamma is satisfied. By the canonicity of the axioms, the canonical model is transitive and left linear. But we need to transform it into an irreflexive tree. It could be very far from it. It needn't be a partial order. We could have, because anti-symmetry could be violated. It needn't be connected, and it needn't be, it needn't be connected. All right, so I take a bidirectionally point-generated submodel of the canonical model. So let's draw a picture of that over here. So here is N. Okay, it doesn't, okay, it's got something like this because of course it doesn't need to be a nice cone because we generate both forwards and backwards. Okay, this remains transitive and left linear. Now we've also made it connected because every point is reachable from this original point. So every two incomparable points must be comparable because there is some part what we can prove that. But so what we've obtained now is, I don't know if I suppose I can just click that. Maybe the recording of all this.
But it's a computer on the go. I cannot do anything because there is nothing open. It says it takes a lot of resources, and, but only the PDF is open. So what can we do? So with PDF is maxing this resources.
It's pretty physical. Okay, so what we obtain is a tree of clusters. Okay, so that I need to prove. Essentially, if we take the equivalence relation of either being the same or you and me seeing each other, then that's equivalence relation of this. And this creates the equivalence classes under this relation we refer to as clusters. So there are three types of clusters. So this is a proper cluster with 3 points in this cluster, we'll see each other. This will be a simple, sorry, I mean, every time I touch this thing, it clicks. This will be a simple cluster. It's a cluster containing exactly one reflexive point. And this is a so-called degenerate cluster. It's a cluster containing one irreflexive point. Okay, so what we need to do is we need to get rid of these clusters. If we look on the cluster level, if we look at this quotient structure, then yes, this thing is a tree, but the structure itself is not a tree. We need to do something to these clusters. So we do the fairly standard bulldozing construction, which I'll remind you of. So if this, for example, is my cluster, I've got 4 points here, which will all see each other. I need to make this linear. So I can take an arbitrary well-ordering of the set. So here I've just chosen U, V, W, and X. Okay, but this won't work. I can't just replace the cluster with U, V, W, and X because in the original cluster, U has W in its past. So there may be some P formula satisfying U, which in this linearization doesn't have a witness anymore in the past. So what I need to do is I need to take copies of this thing and repeat them infinitely to the future and infinitely to the past to make sure that everybody still has bisimilar successors and predecessors to what it had in the cluster. So I will change this 4-point cluster into a countable linear order. And so then the idea is that in this tree of clusters, I replace each cluster with this linearized version. Okay, but this only works in certain circumstances. If we generalize this construction a little more, then we can get much more out of it. So we're assuming we've got a countable frame, which would mean we can enumerate the elements of the cluster. This assumption is justified because I can take an elementary submodel containing the state which I started with by scalar low downwards, and all the properties that I'm interested in are first order definable: the connectedness, the transitivity, the no branching to the left, all of that first order definable. So we're completely justified in assuming we're working with a countable model. And then this I construct a CB, a new, so if the cluster is C, I construct the bulldozed version of C, and this is either of two things. If C is degenerate, it just consists of one irreflexive point, so it stays an irreflexive point. Where if C is non-degenerate, I need to make sure what I'm trying to construct is something where every state in the original cluster occurs unboundedly upwards and unboundedly downwards. So there's different ways of doing this. What we do over here is we simply have a copy of the real number, the rational numbers here, and I'll show you how we get a bounded morphism from this to the original model. So I take then all these new unbulldozed things. I relate two of them, either if the clusters were related, or if they're in the same cluster, but the rational number Q, the rational number component, is less than the other one's rational number component. So it's essentially we make each one linear and keep it in its place in the tree of clusters. And then, now this is what I said, we need to make sure that every guy in the original cluster occurs in a copy unboundedly upwards and downwards. So I could say, well, if the rational number indexed with this cluster is a power of the jth prime, then I send you to xj. And if otherwise, I'll just send you to x0. So it should be many more will go to x0, but that doesn't matter because this will ensure that copies of xj occur unboundedly upwards and downwards for every j. All right. And then this gives us, if I take the union of all those functions, it gives me a bounded morphism from this unbulldozed model onto the original thing. We simply pull back the valuation, and this is a surjective bounded morphism. And so therefore, the satisfaction of gamma is transferred from the tree of clusters to the unraveled tree. Because I use Q in my bulldozing, this is now, well, the branches are not isomorphic. Well, are they isomorphic to Q? They needn't be, and I'll tell you why, but at least they will be irreflexive because I took Q in its strict ordering. Okay, so this is then our result, that this logic is complete with respect to the irreflexive trees. So this plus, if I add density over here, the density axiom, I can do the same construction. I can still use the rationals to do the bulldozing, and I will get a dense tree. What does the density axiom do for us here? Because, I mean, the rationals I'm using for the bulldozing is already dense. Why do I need the extra axiom? Well, what it does is it prevents successive degenerate clusters. Because if I have that in my tree of clusters, then I've got a problem because this thing is bulldozed just to itself. And so then I'm going to have 2 points, one successive, and there's nothing strictly in between. So the density axiom prevents this from happening in the tree of clusters. And so when I bulldoze, any degenerate cluster will be between at least 2, or it can happen in dense way, non-degenerate clusters. So these will be copies of the become copies of the rationals, and we won't have this failure of density. All right. If we want unbounded trees, we should also add future, always in the future top and always in future top or in the part and in the bottom top, to ensure that we always have successors. Because if we don't have that, the tree of clusters could end in a degenerate cluster, and then that will be there. So the result when I bulldoze won't be unbounded. So that achieves that for me. And then if I put all of this together, I get unbounded dense trees. And by Cantor's theorem, these branches will then be isomorphic to the rational numbers, because Cantor's isomorphism theorem tells us that any two countable, dense, unbounded linear orders are isomorphic, and so specifically any such linear order is isomorphic to the rational numbers. Okay. All right, that I've already said. Okay, so now I want to move on to the trees with real branches. Okay, and so, well, we'd like to just, we expect, moving from the rationals to the reals, we get Dedekind completeness. So we would expect that we can distinguish these classes of structures some way, and we might need to add an axiom. So this is what we originally thought we would have to add. Okay, so, and I'll give you the intuition here. So the idea here is, I'm saying at the current state, not P is the case. Then everywhere, if not P is the case, then it's always going to be not P. All right, so in other words, from here on up, we always have not P. Okay, then in the past somewhere, there's a P point. And everywhere, if it is P, then it always has been not P. So from this P point onwards, we always have P. So what we get over here is we get that the set of P points over here is continuous downwards, and it's got a lot of upper bounds, right? It's got all these not P points are upper bounds. There's no P points over here. So this is a set that is bounded above. And so if this branch is isomorphic to the real numbers, this thing should have a least upper bound, right? So I should have some least upper bound over here, some last not P point above all of this. And so this is what the consequent thing says. There exists a point comparable to the current state, which always has been, it's always been P in the past of this guy. Okay, so you should sit over here. So in other words, it always has been P in my past. So I've got no not P point before me, so I'm a least upper bound if I'm an upper bound. And it's always going to be not P in my future. So I am an upper bound. There are no P points above me. Okay, so this is exactly what this would say. And this is what we thought was the axiom we needed to add, and we actually proved that the resulting logic was complete. And I think we realized this axiom isn't sound. Because I'll give you a counterexample. And it's all about the branching behavior. So if I've got here a copy of the real numbers, and here at 0, I add a copy of the interval 0, infinity after 0, then I can find a valuation. So if I make, and let's just decide which one goes which side. Yes, so I make P true on this copy of the real numbers, and I make not P here on this copy of 0, infinity. Then if I take any state over here, suppose I take here root of 2 or something, then not P is true over there. Everywhere, if I've got not P, if I go any point comparable to this one that is not P, so that must be a point in its future, then from there on it's always going to be not P. Okay, so that is satisfied. I do have a P point in my past, just anyone here from 0 downwards on this branch is P. And everywhere, if I've got a P point in my past, well, so everywhere comparable to me, so over here, well, if I've got a P point in my past, then I must be here from 0 downwards. then it always has been P. Yes, because this whole branch is P. So that's satisfied. But now we need to satisfy this part over here, I need to find a point which always in its past is P and always in its future is not P. So it'll have to be over here. I mean, I can't take 0. The problem, what you're going to take is 0, but 0 has both not P things and P things in its future. That's the problem. Anything over here has not P things in its past. So it doesn't satisfy has been P, and anything here has also P things in its future. So this then, this is a tree with branches isomorphic to the real numbers. It doesn't satisfy this axiom. So this axiom is wrong. So I want to compare this to what happens in the linear case. And this is work that goes back to people like Segerberg in the 70s. The linear, the temporal, the priori logics of linear orders were extensively studied at that time, and Segerberg in his essay on classical modal logic has a lot of results on this. So in the linear case, he takes the basic temporal logic for linear orders. So he has to add no branching to the right as well, which we don't have, and simply adds unboundedness and density. And in the real case, it's that logic to which you add this, which is similar to what I've just shown you, but it's a linear version of this Dedekind completeness axiom, which guarantees the existence of upper bounds for sets bound, of suprema for sets bound from above, and infima for those bound from below. All right. But in the tree case, it turns out that the priori logics of the trees with rational branches and that of the trees with real branches coincide. So the logic we've already seen is, in fact, the logic of the trees with real branches. And that takes a bit of work. So I'd like to, but I think the proof is interesting. So I'd like to give you some ideas of what goes on there. Okay, so for brevity, I'll denote this logic. So the basic logic we started out with, transitive, no branching to the left. Unboundedness, both to the future and to the past. And density, I'll denote now as P, priori of the real P sub R. And this we claim is weakly complete with respect to the class of real trees, and also with respect, as we've already seen, of rational trees. Okay, and this is the construction. So again, I take the canonical model, and I take an instant not satisfying my formula alpha, which is now not a theorem of the logic, and I take a bidirectionally generated submodel. Again, as in the previous case, the result is a tree of clusters. All right. Now, what we do is we need to filter this structure. And so what we do is we take the minimal bidirectional filtration of M through the closure of alpha. So if you recall, the minimal filtration relates to two equivalence classes of states over here. I will relate these two classes exactly when some representative is related to a representative in the other class. Okay. All right. So this now immediately causes a couple of problems. So we had a tree of clusters, but it was possibly infinite. Now, so here's a concrete example of such a tree of clusters. This I filtered through the set of all formulas appearing over here. And this is the result. Now, I lose both transitivity and left linearity when I do this filtration. So, as you can see here, Z sees, so over here, on the left-hand side, I suppress arrows that are implied by transitivity because they're all there. On the right, I don't suppress them. I draw all the arrows explicitly. And here, Z is related to XY and XY is related to ST, but Z is not related to ST. So I lose transitivity over there. And as you can see, I very clearly lose left linearity. So we need to go and fix these two things. So, okay, transitivity is relatively easy to restore. I just take the transitive closure. Now, of course, I mean, my filtration theorem told me that, well, everything in the filter that was satisfied at the state is now satisfied at its equivalence class, that state's equivalence class, but now I take the transitive closure. Is that still the case? That's a reasonably standard argument. I can prove that taking the transitive closure is harmless. But, okay, so now we need to restore left linearity. And so what we introduced here, we call an unfolding process, and that's a sort of unraveling on the cluster level. And the important thing here is that we only unravel forwards. I mean, if you're in a bidirectional language and you do unraveling, you typically have to do it in both directions, but that will destroy any sort of trees that you might have. We only need to do it forward here. We do know that what we started with has a unique root cluster. We can prove this. So we start unraveling from the root cluster over here. And what I mean, technically, we see each new state of our tree now as a path of clusters together with equivalence class in the last cluster in that path. Okay, so this is, if we started with this guy, doing the unfolding construction will produce this model over here. All right. Now, there's of course a possible danger over here. If you look at this, if there were if there was a past formula satisfied at this state over here, so there were two past formulas, past P and past Q. The witness for the one past formula may very well live here, and the witness for the other past formula may live over there. Now, this state C4 exists in two copies over here. And the one copy has a copy of the one predecessor, and the other copy has a copy of the other predecessor. So some of these past formulas may have lost their witnesses. But you can prove that that is actually okay, that on every path of clusters, every P formula in a point where you end up with these paths will have witnesses on all of these paths. So doing this isn't harmful, and so satisfaction is preserved. Okay. What we end up with of this is what we, for a lack of a better name, call a pre-real model. So this, and I've ran out of letters, so I need to call the domain S, the relation Q, and the relation B. This model is pre-real if it's finite. It's a rooted tree of clusters. The root cluster and any leaf clusters are non-degenerate, so not any irreflexive point clusters. And there are no degenerate clusters. Okay. So what we have at this point, at that point, was a pre-real tree. And yes, which the lemma states over there. And then we show that every pre-real model is a bounded morphic image of a model with which we call the unrolled model, UR, with branches isomorphic to the real numbers or to the rational numbers, depending on the parameter we put into this construction. So it's a complicated construction, which I will just show to you in a picture. So the idea is, suppose we had this cluster construction over here. So the big clusters over here are non-degenerate, and the small orange cluster is a degenerate cluster. Okay, so I linearize, as I did before, C, come off it. I linearize, maybe I should just point here. I linearize C with a copy of the real numbers. Now, if it's followed by a degenerate cluster, I can just put that, a copy of the degenerate cluster, as after all these real numbers. But if it's followed by a non-degenerate cluster, I can't do that. I can't simply go and make this thing copy of into a copy of the real numbers and place it as a successor over here. Because then I would get something which is not Dedekind complete. I'll have this ascending copy of the real numbers here, followed by another copy of the real numbers. But this set over here will be bounded above by all the elements of this set, but it won't have this upper bound on this branch because this descends infinitely towards it. So this succession of two non-degenerate clusters, if I just do this, makes me break Dedekind completeness. So what I then have to do is I need to take for every real number in this copy, I need to make a real number copy of this guy and put it directly as the successor of each copy. So this is a copy for the number 0. This is another copy for the root of 2, and so on. So you have this multiplication of copies because, well, I mean, now all these guys' success, all this guy's successes, if non-degenerate successes, will have to have copies here and we'll have to have copies here, counted many times. Okay, so what Segerberg with his, and so then what we find here is that each branch in the resulting tree is isomorphic to the real numbers. What Segerberg did with his axiom is he was able to ensure that he had a strict alternation of non-degenerate and degenerate clusters. So every time he could just go copy of the real numbers, upper bound and lower bound. Copy of the real numbers, upper bound and lower bound, which worked very well in the linear case. And the first one was non-degenerate and the last one. So you ended with 2 copies of the real numbers and strictly alternated this with points in the tree. So, and that's what we initially did when we had this unsound axiom. But yes, it's not sound, so we had to come up with the other plan. In other words, this construction over here. So then, as you would see, I mean, there's really nothing essential about using the real numbers with the strict order over here. I could also have used the rational numbers. For example, I could have, if I had the reflexivity axiom in the logic, I could have used the reflexive versions of these number systems as well. So that's then our theorem. This is weakly complete with respect to the class of all trees with real branches. We need this filtration construction, and this is where the restriction to weak completeness comes in. Right? We can't do this for arbitrary sets of formulas, because if we had to preserve the set of formulas, the filter would be infinite and the filtration would be infinite. And we haven't been able to, it's an open question whether this logic is strongly complete. So any of you are keen on looking at that. I think that's a typo over there. This should be the reflexive real numbers. So if I add, okay, and there's a bit of a summary of some of these logics. We can, all of the logics considered over here, so these are the logics of all irreflexive trees, the unbounded, dense versions of these. This should be a T, I think the irreflexive rationals, the irreflexive reals, these are all the reflexive versions. Unbounded, dense, isomorphic to the real, irreflexive reals, irreflexive rationals. All of these are decidable via Harrop's theorem and via a finite model property. Of course, they don't have the finite model property with respect to trees. That's impossible if this thing needs to be unbounded, but they do have finite model properties with respect to classes of cryptoframes on which the axioms are valid. So all decidable. I have no idea about complexity, so anybody is keen on that. These were basically the non-discrete trees. So I'll give you an idea of, well, I still have about 5 minutes, I think. So this is one paper. The second paper looks at discrete classes of trees. So by forward discreteness, we just mean that, well, and of course this has to happen on every branch. If I've got a successor, then I must have an immediate successor if this isn't an immediate successor, I must have an immediate successor in between, on and so forth here as well. And backwards discreteness just with the inverse of the relation, and discrete if you've got both these properties. So to axiomatize the logic of the discrete trees, we were unable to do this with axioms only. So we needed to introduce these context rules in the style of Gabai. So the irreflexivity rule is the one that, that you probably are most familiar with. And so which basically says that if I've got not P and has been P implies phi, then I can conclude phi as long as P is not a variable occurring in phi. Okay, and for those of you who haven't seen this, I'll just go through why this works on irreflexive trees. And the easiest way is to do it contrapositive. Suppose this is not satisfied on an irreflexive tree. Then I can show, or not validated on an irreflexive tree. So there's some point in evaluation where this guy is false, but then because this is irreflexive, I can change the valuation, what it does to P, and make this true over here, because I simply, this is my point W, I simply declare V prime to send P to the whole domain other than W. But because W is not a successor of itself, well, P will be true at all its successors if it has any, but P is certainly false. So this is true, and so this was false, so true implies false, so this is also false over here. And so this to the proof theorists, Andrea and Giuseppe, we need to use these rules. And so the forward discrete and the backward discrete rule work on similar principles. Lots of people have looked at these context rules. Goronko has a paper on them. Feynman has this rules as anti-axioms. Yeah, so we can do this. We use these to make sure that the canonical model has enough maximal consistent sets with additional properties, so that we can build our satisfying model in a step-by-step way from these maximal consistent sets with the additional properties, which then guarantees that the final model will be discrete and irreflexive. Now, we don't know, so we're currently wondering, are these rules perhaps admissible? Because famously in Gabai's case, if you just add irreflexivity, yeah, it's admissible because you can unravel the model and do the completeness result also without the irreflexivity rule. But well, we have not been able to do it without these rules. They seem somehow essential. So those of you who know about admissibility of rules, I'd be very glad if you could enlighten me here. And also people interested in refutation and what do you call it? Refutation, the combined system?
Hybrid system.
Hybrid systems, where you do both refute and derive formulas. I mean, these things work essentially on being able to refute P implies HP, right? Or sorry, HP implies P. All right, so it's about satisfaction, not about validity. So I was wondering if there are connections over there. But okay, I think that's more or less what I have time for. So thank you very much for your attention.
Any questions?
We looked at whether there are decision procedures for some of these logics. Well, we know they are decidable, but we have no effective decision procedure or practical decision procedures for them. But I'd be very interested in this. I mean, so they're all decided. I mean, in the discrete case, there's one or two open questions. In that first table that I presented, yeah, they're all a finite model property, finite axiomatizations. But yeah, I've got no idea about any bounds on complexity over here.
Other questions? So I have a question. Do you know any results about undirected trees? So
Yeah.
these would be, there's no directionality. You have forward and backwards in yours, but you would axiomatize them with a betweenness relation, which would be a ternary relation. And the models would be undirected trees where the paths can go in any
So just acyclicity, is that all we're assuming?
Acyclicity, yeah,
We're assuming. So,
Yeah.
Okay.
Yeah.
No, I don't know about any results on that. So would it be a modal logic axiomatizing this between this relation, or
Yes, something like that.
Okay. No, but I'd be really interested to look at that.
And you could imagine continuous models of the kind we talked about.
Yes. No.
In addition to the usual discrete models.
Very interesting direction, possibly.
Yeah. Okay, thanks again.
Thank you.
We'll continue again in 7 minutes.
I think I will ask later. No, maybe the PhD thesis of your
Yes.
yes.